Greetings from Teton Valley, Idaho. My name is Eric Wolf. I'm a research scientist at the University of Colorado in the Laboratory for Atmospheric and Space Physics. Today, I'm going to talk about the NCAR Community Earth System Model, applications to exoplanetary atmospheres with the ExoCAM extension. My contact information is listed on the slide. This is for the TRAPPIST Habitable Atmospheres Intercomparison Workshop on September 14th through the 16th, 2020. So, the National Center for Atmospheric Research is located in beautiful Boulder, Colorado. Shown here is the Mesa Lab, an IMPE designed building located high up on a hill above the town, just west of Boulder, right underneath the iconic Flatirons. So NCAR provides us with the Community Earth System Model, which is a climate system model which couples together components of the atmosphere, the land, ocean, ice, and whatnot to give us a full picture of the Earth's climate system. So NCAR was established in 1960 as an Earth Modeling Institute. Its first public release of its climate model was in 1996. NCAR is supported primarily by the National Science Foundation. Unfortunately for us, NCAR has no institutional support for exoplanetary modeling due to their mission statement being focused on societal relevance of climate and its effects on the present day. Still, that hasn't stopped many people from now using CESM for planetary purposes. This slide shows the general CESM architecture. It is a multi-configurable code. It is easily modifiable, though that may be a relative term given the complexity of 3D climate models in general. So first and foremost, we consider the atmosphere component, CAM, the Community Atmosphere Model, which has 4 different flavors now that are available, version 3, 4, 5, and 6. So CAM generally controls the radiation and also the moist physics used in the model, clouds, convection, things like that. There are other versions and configurations in the atmosphere model, such as WACM, which has an upper atmosphere extension up to 140 kilometers in one version, up to 500 kilometers in another. There's a KARMA add-on, which is a sectional cloud and aerosol model, which has been used to model the details of ice clouds, model volcanic eruptions, and things like that. There's also the Mozart chemistry model, which has several different schemes to model chemistry. Then the atmosphere model is accompanied by the sea ice model, which prognostically can calculate sea ice. The land model, which has a rich variety of different surface types if one wants to dive into it. And also the ocean model, which is available both in the dynamic ocean, full dynamic ocean, and also with a slab ocean option. And all of these are connected together through a flux coupler, where energy is, the energy terms between all the different components are passed between each other in a self-consistent way. Finally, there is also the Paleo Toolkit, the NCAR Paleo Toolkit, which allows one to change the lower boundary conditions. And give you a warning, this is actually a lot more complex than it sounds. Well, it's pretty easy to make a 100% land planet or 100% ocean planet. When you get into mixing and matching complex continental configurations, it can get a little bit hairy. So that the NCAR Paleo Toolkit comes with a warning. So despite CESM being an inherently Earth-centric code, it has been used by many now to study planetary and exoplanetary applications. So first I list here deep paleoclimate. So near-term paleoclimate back the last 1,000 years or so is close enough to being Earth-like that even NCAR will do near-term paleoclimate. But deep paleoclimate veers outside of their realm. And that's when we start thinking about things such as the Fate-Young Sun paradox for Earth, snowball Earth initiations, Other studies have been done with Wacom Karma, a very interesting study of an asteroid hitting the Earth and causing the fallout responsible for killing dinosaurs. CAM has also been adapted for Mars, so both present-day Mars and early Mars, focusing again on the faint young sun paradox for Mars, which is more intense than for Earth, and also dust and cloud interconnections on Mars, which are quite complex. There's also a CAM Titan version, which has been used to study the microcloud, haze microphysics rather, but also match Cassini-Huygens observations. And here's also a list of planetary papers used for exoplanets. And I should say, on both the last page and this page, I apologize if I've missed your paper. There are many papers that have come out on planets and exoplanets using the NCAR model. So these are incomplete lists, I'll say, to cover my bases. So many studies have used what I'll call native flavors of the NCAR models. As I said, the NCAR model is multi-configurable. It's not that hard to modify. Jun Yang's group, Aomawa Shields' group have both done a lot of work with the NCAR models in CAM3, CAM4, and also CCSM, which is a predecessor of CESM, which includes a dynamic ocean model. Other studies have been done, listed here. Some recent work that Howard Chen will be presenting later in the workshop, using WACM, CAM and WACM to study the chemistry of extrasolar planets. And then at the bottom here, I list a number of papers which use this ExoCAM modeling extension, which I'm supposed to be talking about. Can't talk about ExoCAM though without first giving background on the NCAR modeling suite in general. So many of these ExoCAM studies have focused on habitable zones, tidally locked planets, atmospheric circulation regimes, moist greenhouse climates, parameter studies, things like planetary gravity, solar insolation, stellar types and its effect, FG, K, and M dwarf systems, and so on and so forth. So ExoCAM, what is it? So ExoCAM is a model extension for the NCAR CSM that supports a variety of exoplanet climate modeling applications. It's easily installable on top of CSM version 1.2.1. If you're familiar with the code, you'll know that the way CSM operates is you have your primary source code, which you download from NCAR, which resides in one side of your directories, and then it also has a separate directory for user modifications that is separated from the core code that you download from NCAR. So ExoCAM, you can take its source code modifications and copy it easily into the appropriate source mods folder, as it's called, and then coupled with a suite of initial condition files that are provided, nameless files, which specify different initial condition files and settings that you need, configure scripts, etc. It's easy to build and start running CSM for exoplanets using the provided ExoCAM files. I also provide with ExoCAM a variety of initial conditions and also in data analysis scripts, so you can do simple things to get yourself started, such as determining when energy balance is reached, and so on and so forth. So where did ExoCAM come from? ExoCAM grew out of my graduate work and early PhD projects, first in NESSF graduate fellowship studying the faint young sun paradox for Earth, then a NASA Planetary Atmospheres Program grant on habitable zones, which is now, I think, Planetary Atmospheres has now been rolled into Habitable Worlds and other programs, and also a Habitable Worlds grant with Ravi Kaparapu and Jacob Hakamisra to study the inter-habitable zone for M dwarf stars. So through these projects, gradually the source code modifications evolved into a product which I can provide to the community to use as well, coupled with CSM 1.2.1. And sort of the ethos we're going for here is that climate modeling is hard. There's a lot more interest now in climate modeling of extrasolar planets. So my hope is that ExoCAM is fairly easy and straightforward for someone who's interested in exoplanets but is not necessarily a climate modeling junkie, that they can pick it up and they can start running and doing cases without too much, too much consternation. So what can ExoCAM do? So it's a flexible, multi-configurable terrestrial exoplanet model. Out of the box, it supports atmospheric compositions of nitrogen, water vapor, CO2, methane, H2, with an upgraded radiative transfer scheme that is flexible, so you can modify it more easily and also pull out different outputs of the radiation fields more easily than in the native versions. Surface pressures are supported between nominally about 0.25 bars and 10 bars. Temperatures nominally between about 100 and 500 Kelvin. Surface types currently supported are aquaplanet slab oceans, efflux oceans, land planets, Earth continents. Numerous stellar spectra are provided, from TRAPPIST-like stars all the way up to F-dwarf stars. The orbital parameters can be modified. You can vary eccentricity, obliquity, the solar constant. You can vary the rotation rates, make the planet synchronous, asynchronous, change the surface gravity. These are standard options for exoplanetary 3D modeling codes, of course. ExoCAM currently can be run with the finite volume or spectral element cube sphere dynamical cores. Currently, it can be run with the CAM4 physics package in the background, and then with the Karma microphysical model turned on for haze aerosols, if you wish. So other modifications around the edges, I'll say, so in the finite volume dynamical core, convection schemes, and elsewhere, they've been modified slightly to improve the numerical stability as climate diverges from modern Earth, so the models don't crash, a familiar problem for any planetary climate modeler. With more work, but not an onerous amount, one can access some of these other modules available from NCAR, such as upper atmosphere models, the dynamic ocean model, CAM5 physics, variable resolutions, and other features, which are not too hard to switch on and off within the context of ExoCAM with a little extra work. So, as a kind of a diversion, have you ever wondered what a supervolcano would look like on TRAPPIST-1e? Yeah, I thought so. So this is just a simple add-on to actually the TIE Benchmark 2 case, where we inputted a plume of water vapor, roughly approximate to what you'd expect when Yellowstone might erupt, into the atmosphere, and we let it evolve over 180 Earth days. And you can see here in the bottom, specific humidity in a cross-section along the equator, and also vertically integrated precipitable water. Novel studies like these are what we envision as fun things that could be done with ExoCAM as we veer very far away from standard Earth CMIP style runs and into the fun and wide world of exoplanets. One of the interesting things to fall out of this just little play run that we did was water ends up getting stuck up in the stratosphere. So you have a moister stratosphere than a troposphere in this case. So just to touch on what's the latest happenings with ExoCAM. So the radiative transfer packages that are available, have been available with it, have grown long in the tooth over time, one of which I developed as a grad student, another of which I developed circa 2015. So now these have been completely updated as of about 2 weeks ago to HITRAN 2016 for H2O, CO2, and CH4, a variety of collision-induced absorption from the latest references. We use now, instead of somewhat clunky traditional mixed gas K coefficients, to a on-the-fly equivalent extinction gas overlap method inspired from David Odmundson's work. And in this case, we dynamically select the dominant gas in each spectral interval and in each grid box in the model, and it's surprisingly not that slow, and it's workable. So here's a few examples on the bottom from the 1D column conformations of the model for a water vapor rich atmosphere and also for a CO2 rich atmosphere. So this is ready to go. Anybody who wants to be an early adopter, please let me know and help me find out where some more of the bugs are. So future plans, future funded plans, not just ruminations. I've been funded by Habitable Worlds to start porting an old Mars Cam Karma version upgraded into the framework of CESM version 2 and ExoCAM with a science focus on exploring cloud microphysics, dust, and their coupling using Karma for early Mars in particular, but there will also be applications for present day Mars. And then 2, a SEEK-funded grant to explore H2-rich exoplanets, super-Earths, and the like, with a science focus on relevant observable planets for JWST, i.e. not necessarily habitable worlds here. And then proposed in the context of the ICAR projects, we have a number of other applications proposed, but we'll have to wait and see what happens there. So finally, where to get the code. The primary source code has to be downloaded from NCAR, CESM version 1.2. The ExoCAM extension is available from my GitHub site. And then you'll see it's split in 2. There's ExoCAM and then ExoRT. They go together. I split off the RT into a separate distribution because to allow one to run it offline separately. Finally, there are other planetary cam versions. Mars and Titan are available on this wiki site below. So thank you for listening to my talk. I'd also like to thank my dog for not barking during this recording, and I'd like to thank Kaufman's OK Tires in Driggs, Idaho for saving my vacation. Thank you.